Okay, shall I start?
Minimize it.
Hello, everyone. So today we are going to talk about NLP. This is my field of research, so I'm super excited about today's meeting. So the title of the slide is An Introduction to Natural Language Processing. Well, basically, I'll go through the evolution of NLP, right from the bag of words model to the latest things like ChatGPT and GPT-based models. So Lee will be presenting with me. So let's get started. What? Why is it not? Okay. Yeah, now it works. Yeah, so what is natural language processing? Well, if I had to put this in a single sentence, it would be this is a branch of artificial intelligence where we design and implement algorithms that can understand human language and can interact by using human language. Now, the easiest way to understand what we do in this field called NLP is to look at its applications. And we can classify the applications into 4 categories. So the first category is called sequence classification. In this case, our model will take a sequence of tokens. And by the way, whenever in this presentation, I'm going to say tokens, it will be words, because in natural language, in a sentence, the tokens are words. So in this particular task called sequence classification, the model takes a sequence of tokens and spits out a possible class corresponding to that sequence. Examples could be sentiment analysis, and a document classification. Now, the next type of task we have here is pairwise sequence classification. Here, instead of giving one sequence, we give the model 2 sequences. And output is still the same, a set of possible classes. Now, examples could be textual entailment, document similarity computation, etc. The third kind of task we have is called word labeling. So here, we will predict a class for each token present in our input sequence. The most common example is parts of speech tagging. And also we have named entity recognition. Finally, we have something called as sequence to sequence task. Here, the model takes in a sequence of tokens and spits out another sequence of token. The best example for this would be translation task. And obviously we have summarization and text generation too. Now, let me explain these things using one single example. So here's the sentence: I really like David's cat. Now, one task could be translation. So what is written underneath is the same sentence translated into Bengali. So it says, Ami Davider Belar Pochond Kori. So it is just the translation task. Another NLP task is sentiment analysis. Here, the model tries to predict if the given sentence carries a positive sentiment or negative sentiments. Obviously, it's a positive sentiment. Then we have the word labeling task, where we just do the parts of speech tagging. And finally, we see an example of pair-wise classification, where we take another sentence, David owns a cat, and if someone gives you these 2 sentences, we can say that the second sentence follows from the first sentence. So this is called an entailment, and the task is called textual entailment task. So here we have tried to show all kinds of NLP tasks in a single example. Now, let's move on to the evolution of NLP. So in the earlier days of NLP, what people used to do, it is called bag of words. So the idea is actually very simple. You take a document and try to convert each word as its own feature. So suppose you have got a document of like 10,000 words and it has like 100 or 2,000 sentences. Now you go over each of the sentences and take the words that are present in that sentence. So suppose you have a sentence like, I like David's cat. So the words I like, David, and cat will be one for that particular sentence, but all the other words for that particular row will be zero. And Lee will actually show that how to do that. And the method is actually called one-hot encoding, because we are either assigning one to the feature or zero to the feature. Now, the obvious problem with this kind of approach is the vectors are huge. Because as I mentioned, if you have a document of 2,000 sentences, the number of words can cross like 10,000. So will be the number of features. Now, another problem with this kind of thing is, if you take a vector for a particular sentence and a vector for, if you take a vector for a particular word and another word, they will be orthogonal to each other. Why? Because if in a sentence the word I is present, it will be one, but in another sentence, if I is not present, that corresponding dimension will be zero. So if you imagine a higher dimensional space, they will point orthogonally. They will be orthogonal to each other. So the similarity computation will be really hard, because in NLP, most of the similarity computation depends on the dot product between the vectors. And another problem with this kind of approach is the context of the sentence is not taken into account. So as you know, in the current state of the art, there's something called attention mechanism, which takes the context into account, which we will get into that. But obviously, this kind of thing is not present in bag of words. Now, we also have something called as term frequency and inverse document frequency, TF-IDF for short. Now, this slightly improves over bag of words, but these are not that great too. Now, after that, we see a revolution in NLP called word vectors. Now, the idea here was, what if instead of assigning each word as its own feature, we represent every word using a fixed length vector, say 100-dimensional vector. So the like usefulness of this technique is the number of features never cross 100. So you take every word in the dictionary and you can assign it to a 100-dimensional vector. So, and the similarity computation will also be better here, because they won't be orthogonal to each other. Now, the first paper that introduced this technique was called What-to-Vec paper. And the famous result that everyone shows is this graph here. So here they have taken 4 words, king, queen, man, woman, and they have taken the PSNE representation of these vectors to show it in 2-dimensional space. And what we see that direction corresponding to the blue arrows has the notion of gender, because you see like king to queen and man to woman. Now, we also see another interesting result here. We can actually perform algebra on these vectors, because if we take the vector of the word king and subtract the vector of the word queen, that will be very close to something, to the subtraction between man and woman. And after the What-to-Vec thing came up, we also saw a lot of other word embeddings. The famous ones are Glove and fast text. So like it's not unsupervised, they call it semi-supervised, because like to the basic idea of this word vectors is a vector for a particular word would be similar to its neighbors. So say it wants to generate the word vector for king. So it goes over every document that has every sentence that has the word king. it looks at its like nearby words. Ideally, they define a window length and they check at its context and try to predict what would be the vector for king based on the words that appear in the neighborhood of king. So that's how it does it. So it's not like unsupervised. It's not like supervised either. But yeah, like it has some kind of, it comes up with the supervision by itself. So it's like semi-supervised. So now moving on. So once we had the word vectors, people tried to use word vectors with neural networks. So in this particular slide, what we can see is they took the word vectors and they pass it to something called convolutional neural network. Now, traditionally, they used to use it for image processing, but once the word vectors came up, they treated these word vectors as features and applied the convolution trick on them. Now, another interesting thing people did was something called recurrent neural networks. So recurrent neural networks are designed to deal with sequence tasks. So obviously, like as we mentioned, as we saw in the example, in NLP, every sentence is treated as a sequence. So you see here, W1, W2, W3, W4. These are nothing but the words in a sequence that is forming a sentence. Now, there is some terminology involved here. This part where we take the word vectors as input, we call it encoder. Now, after passing through each of the states, we get some abstract representation of our input, and then we pass this abstract representation to our decoder. Well, decoder is like very similar to encoder, but this does not have access to the raw words. It gets only the encoded information from the encoder, and then it tries to predict something. Now, after that, NLP field saw another revolution, and that's called the attention mechanism. Now, the main drawback of this mechanism where we had the RNN thing was it couldn't deal with long sentences. Because you imagine, suppose you have like 100-word or like 50-word sentence, when it will reach here, it will lose the information that came like 50 stages before that. Now, to avoid that problem, what this paper does, what this paper did with attention mechanism, to predict an embedding for a particular word, it looked at all its context and they combined their vectors to produce a new vector. And how did they combine? Well, it just did a linear function. So it would multiply every vector, every word of its context vector, and they will just sum them up. So this was the like big revolution in NLP. And after that, like around the same time, we also had another thing called ELMO. So this architecture was actually similar to the RNN architecture. They used the LSTMs, one type of RNNs, but here they considered the context of the word to generate the vector of a new word. So it was different from this architecture because in this architecture, people were not considering the context of the word. And also here, you will see the arrows are bidirectional. So it would look at the sentence from both directions, as opposed to the RNN word, it used to look at the sentence only in the future. So it would parse the sentences like left to right. Now, after that, obviously, we had the big revolution in NLP, the transformers. Well, actually, the paper here that introduced attention mechanism, after some time, another paper came up that first proposed that we only need attention mechanism. The paper title was "Attention is all you need." So it completely like replaced the encoder decoder thing of the past that people were using at the time. So they said, okay, we don't need the encoder decoder thing. We will only use the attention mechanism and make our work. So after this paper came up, we saw BERT that really kicked off the game of like large language models. And after that, we saw Roberta from Facebook, Alberta, DistilBERT, Multilingual BERT, and many more. And of course, the latest thing is GPT-2, 3, and 4. And one interesting fact is that GPT-2 actually came before BERT, but the major, and these two architectures are, by the way, very similar. But the major difference between GPT-2 and BERT was BERT looks at the sentence from two directions. But GPT-2 used to look at the sentence from only one direction. That is, it would parse the sentence from left to right. So yeah, that was the presentation. Now it's demo time.
Switch over to the demo.
Oh, yeah.
It's funny that Sujan went over the entire evolution of natural language processing, because we're about to go all the way back to the start of it for the introduction. Because, you know, if I threw you guys at language transformers and state-of-the-art stuff, you would not learn the basics or anything. You're just like, okay, a large language model can do it. So we're actually going to go down to the raw basics of natural language processing. We're going to go towards even like, I'm going to be using bag of words and like, you know, one hot encoding, which, you know, is outdated now, but it will teach you like the fundamentals of what's actually going on. So first, you know, we import libraries as we always do. We're going to mostly be using Natural Language Toolkit, which is like, I'm going to say outdated now because of how fast large language models are going, but it was the premier like Python package to do natural language processing. But nowadays it's very basic, but it'll still give us the fundamentals. So here we got to download a bunch of stuff for NLTK to work, because really it's downloading a bunch of corpuses or bags of words to work with. So like when it does sentiment analysis, all it's using is a huge dictionary of words with their corresponding sentence or sentiment, and it just looks up what the sentiment of that word is. So we're going to import data. We're going to go back to our old friend, Project Gutenberg, and I got 3 texts for us. I got Alice in Wonderland, I got Moby Dick, and I got Romeo and Juliet. So 3, you know, classic texts, but of, you know, different areas of literature. So first, you know, we can read in our data. So what we did here is we read in sentence by sentence, or it's not quite sentence by sentence, it's actually going by every break line. So like some of the sentences are broken up, but we'll deal with it. But anyway, just a list of, you know, Alice in Wonderland here. And so the first thing we need to do is we need to clean our data. So how do we turn, here is a paragraph of text, and say, hey, computer, like, understand this? Like, we first need to clean this up, because if you just like, this is not an intelligible thing to a computer, it's just a bunch of text. So the first thing we need to do is we need to tokenize. So basically tokenizing just means you need to split your sentence up into the individual words. So here, if I run this and let's add code, let's just look at token Alice here from, I think it starts on line 55. No, token, no, problem with live coding. So here, instead of the first sentence, which is large rabbit hole under the hedge, it's now separated by a word. So large, and then every indice is a word. So that's what we mean by tokenization. It's basically splitting up our sentence into its individual words. And then what we're doing here is stop word removal. So stop word removal is like mostly articles of language, or like something inconsequential to the actual meaning. It's just connective tissue that like us as humans need, but for a computer, it doesn't really. So these are like is, and the, or here I printed out the entire, or not the entire, but a snapshot of Natural Language Toolkit's corpus of stop words that it will remove for you. So it's like I, me, my, myself, we, are, ourselves. It's a lot of articles. So then I can clean up our data. So now here is our clean Alice in Wonderland without stop words. So it's getting less intelligible to us as like humans, but it's now getting more intelligible to a machine, because now we've tokenized it and we kind of taken out irrelevant words to the actual meaning of the language. So now we can go into additional cleaning steps called lemmatization and stemming. It's basically like if you have prefixes or suffixes to a word, they don't modify its meaning, just like what tense it's in. So if you have like run or running, those are really conveying the same words, but if you were to give both those words to a computer, right, it has no idea that they're actually the same word, but in, different tenses. So there's two things you can do. So one is stemming, which is literally just like cutting off the prefix / suffix. And then there's one called lemmatization, which is finding, the word and then substituting for its root word that is in like a neutral tense. So if I have the word studies and I do stemming, it's now study. But it would be the same stem for studies, studied, studying, like but the thing is you would miss the word study with the Y, right? Because those two words are not the same. So then a computer would, take them as two individual objects. But if you do lemmatization, where we replace it with the root word, anything like studies, studying, studied, it would turn into study, the root word. So it's usually preferred to do lemmatization over stemming, even though I think these are kind of inconsequential now because we found that large language models can handle this without doing it. But in base natural language processing, lemmatization when you can. So here, take the lemma of all of our text so we can go into our analysis. So now we have some clean data, right? It's lemmatized, we took out the stop words, it's tokenized, so we can actually start to do some surface level analysis. So one of the most basic but surprisingly useful forms of analysis is just term frequency, which is literally what is the most like word or the most frequently used words in your text. You see things like word clouds and stuff to like, visualize this, which I think there is a word cloud package in Python. Yeah, there's. I haven't used it, but I've seen it used, but I just did a kind of a brute force listing. So we can do term frequency for Alice, right? So we have the term used and the number of times it's used. So it's said, Alice, little one, Gutenberg's in there, which is probably just like when it was like describing what the text is from Project Gutenberg. And then we have Moby Dick, and who would have thought that the word whale is the most used word in Moby Dick, because it's just about a guy chasing a whale. And then we have Romeo and Juliet. So we have Romeo is actually mentioned more than Juliet. That might say something, I don't know. And also thou is said more than than Juliet. So Juliet didn't even take the second spot. It's thou, then Juliet. Yeah.
Montague is so there's two main families, the Capulets versus the Montagues.
Yeah. No, yeah, it's Capulets. So the Capulets, was Romeo a Capulet?
Romeo, I believe Romeo was a Capulet.
Yeah.
Juliet is
Montague.
families.
Yeah, and the families are feuding. So I wonder because Romeo was, mentioned more, if then Capulet was also mentioned more, because Juliet was like not even more used than thou. So other way around. Okay. We don't have enough literature nerds, so we gotta look it up. And then we can do something, we talked about part of speech stacking, which is saying like, okay, this is a verb, a noun, or whatever. You can look up all the part of speech tags here, which there's actually way more parts of speech than I thought, because I speak English, but I don't really know it. So if you look, here's all the parts of speech tags that Natural Language Toolkit has, and it's just like adjective, comparative, adjective, superlative, there's a couple even verbs. There's verb, gerunds, judging.
ING is a gerund.
Yeah, I don't know that.
English is actually considered the hardest language to learn. If you don't know it previously, I've heard that the first English because English doesn't add with the word lot, the F sound is, but elephant is EH, but enough is EN.
Okay. So yeah, I looked at all of the verbs, or we could look at all the nouns or whatnot. It's weird. It counts God as a verb. Can God be used as a verb? I thought it was always I God you. What in my God? That's still referring to fear God. No, it's always a noun. But through say queen, this must be old language. I'm showing how illiterate I am. I don't know this word. I don't know my parts of speech, but you can let's just look up and N was nouns, so we can get like the top like nouns used. So this is Moby Dick. So ship, sea, man, boat. Yeah, that's basically what it's about. Ye, yeah, time. Head, captain. Yeah. So you read these 10 most used nouns, and you don't have to actually read the book. So you know what it's about. Yeah. And then we can do sentiment analysis, which again, this is a brute force sentiment analysis, or like we call it a lexical, which is just like you have a dictionary of sentiment. Some of these dictionaries are actually made by hand. We really have like a group of an interesting algorithm. It's called a graduate student. And you make them just read a bunch of words and then say what they think the sentiment is. And then you have like a group of 10 people do it on the same words. Yeah, and then like sum them up. For this one, I think it was a semi-supervised thing where they had some like hand labeled words, and then they had a algorithm like learn the words around it. So it wasn't quite as manual. But here you can download a sentiment analyzer from Natural Language Toolkit. And then it will actually give 3 scores. It has a negative score, a neutral score, a positive score, and then a compound. So you can get like, do you want a binary? Do you just want to know if it's negative, positive, or neutral? Or do you want the compound? So here, like kill, neutral, or not neutral, bad sentiment, love, positive sentiment, and then I just put like spoon, just like a thing. It's a neutral sentiment. And yeah, the cutting edge is definitely using a large language model to do this. Like in my thesis, I used Roberta Large to do my sentiment analysis. It took a long time. Like at least a lexical approach is like very fast because all you're doing is dictionary lookup. You're not actually like evaluating a model, but it's not context dependent because you have no contextual information. It's looking literally what you do to classify a sentence is go word by word, take the sentiment score of every word in the sentence, and then take the mean of that. And that's like your sentiment score. So here I took the sentiment of all of our texts, and then I want to know for Romeo and Juliet, a very like tragedy, and do they even call it comedy? Like technically it's technically it's like comedy because comedy just means like it reverses like emotion or something like that, like the classical meaning of it. So the most positive sentence in Romeo and Juliet is doth grace for grace and love for love allow. And then, the negative one is alack the day, she's dead, she's dead, she's dead. Which I mean, yeah, dead, dead, dead. Yeah. So if you think about how this lexical sentiment analysis is working, right? Every time it sees the word dead, it's like adding negative value. And then when you sum it up, right, or hear grace and love, positively sentimented words. So just seeing, oh, these words have good like positive sentiment. But this approach really fails when you have something of mixed sentiment. Like if you say like I love to kill people, right? It's taking like love as positive sentiment and kill as negative, and it'll actually say like the sentiment of the sentence is actually neutral, and it doesn't understand like with the lexical approach that like the positive word is amplifying the meaning of the negative one. Just use ChatGPT, I guess. So. So now we can get into modeling because we've cleaned everything, and we did some surface level analysis, but really the power of natural language processing is the modeling aspect. We can have computers kind of like understand human language. So first thing we're going to do is embeddings. There's a ton of embeddings like we did like fast text, word2vec. We're going to go with the most basic one, which is the one hot encoding. So we have a count vectorizer from, I believe this is sklearn. So very low level. This was literally the first ever like conceived of like embedding system. So yeah, we're kind of in the past, which to be fair, in the past for natural language processing is probably like 5, maybe 10 years. So here we have our first clean lemmatized sentence from Alice in Wonderland: large rabbit, whole hedge, and large rabbit. Every word in the sentence gets its own vector where 1 is present. This is because we only have a single sentence. If we had multiple, it would take the entire, set of words, and then if you had a sentence with like 2 of the words, it would have like 1 wherever those words are present in the entire vocabulary. So we can vectorize all of our stuff in a very basic way. And even with just a basic vectorization, I clustered all of the sentences in Alice in Wonderland together. It was like a several thousand dimensional vector because that's how many unique words are in Alice in Wonderland. So I just used PCA to get this down to 2 dimensions. And we see that there are like very distinct clusters in this Alice in Wonderland text. So we can actually, I used a quick just k-means or canon something, k-means to cluster these. And so we can actually check out what these clusters are. So here we can go through our clusters. So one of these clusters, I believe, is every single sentence that has something to do with Alice or contains Alice. So here we found one of our clusters, and it's every single one of these sentences has to do with Alice. We can look at other clusters. One of them is like, I think this is every like time she says something without her name being mentioned. So it's like there's a bunch of like she says in there, a lot of quotation marks. So there's a lot of like the dialogue really clustered together. I think one of these actually captures all of the words that aren't part of the story, but part of the like description. So like this ebook is used for whatsoever, you may copy it, blah, blah, blah. Like this is all the like disclaimers beforehand, and they all cluster together because they look different. Their vectors look different than the actual vectors from Alice in Wonderland, which is it's pretty cool. Even with very, we're using like at this point the like caveman tools of natural language processing. We're still like finding like decently interesting results. But now we want to go to something at least more recent. So we're using GPT-2, which is GPT-2 the last one that's publicly available, or is 3?
3 is publicly available. Like, okay, no, you can pay for 3 and finding it. You have to pay for GPT-2 to find.
Okay, so GPT-2 is the last free version of GPT. GPT-4 is definitely proprietary because that's the newest thing. GPT-3 you can get as long as you pay for it. But as broke grad students, we're obviously going to use GPT-2. So a couple generations behind, but it will work for our premises. So what we're doing is we are seeding this with a prompt. The prompt is the first 10 lines of Alice in Wonderland. And we're saying, hey, here's 10 lines. Can you predict what the next 10 lines or the next?
You have to subtract that
from
so the maximum length is 256. So it would generate 256 minus
the prompt length. Yeah. So let's just I'll run. We'll do it live. So here's the prompt, and it's thinking about it. It's going to generate actually 10 different generations, right? So 10 different interpretations. So it's like, take this prompt. Okay, so what do we get with this? Generated 0. So the prompt is this. How did it end? So first, she tried to look down and make out what? Something. A lump at the top of the rabbit hole of her stomach. Interesting. The place where they were standing on, I don't know. So here is a bunch of just like times it tries to read the prompt and like continue it in context. Which, because this is a couple generations before.
Generation 4, that is a little bit makes sense. the bottom half of the rabbit hole with her eyes closed. She tries to make out excitement.
So if you remember, we tried to do the same thing with an RNN, but with the character sequences, it was kind of like drunk text. At least it's like, intelligible. It looks like a person might have wrote it, but it does miss context because to be fair, we only gave it the first 10 lines of Alice in Wonderland. Like, but sometimes I remember we generated one where it treated the rabbit hole as a person and like assigned person to it. So it's like, and then the rabbit hole said to Alice, like stuff like that. So that's pretty good. I wonder if we let it generate.
Correct, by the way.
Yeah, grammatically correct. Do you know how much GPT-2 was trained on? Like, it's probably trained on a lot of stuff. 4 terabytes.
4 terabytes, yeah.
Not bad. I mean,
That's
not much compared to the new. GPT-3 was 45 terabytes of data. I don't even know if they released what GPT-4 was. It might be proprietary. Because GPT-3 was still all publicly available text on the internet. Yeah. But I wonder, because if you had GPT-4, which has probably seen all text that exists on the internet, which includes Alice in Wonderland, I wonder if it would. Yeah, because I wonder if you gave it to a large language model who has seen the entirety of Alice in Wonderland, if it could just regurgitate it back to you, like.
It might, but I think it won't, because like that would be like memorizing too much.
Yeah, because it'd have to recognize that. Yeah, that's true. but we should have like Chat GPT, like give it, you know, the first 10 lines and have it try to generate the rest of the story and see how much it lines up to the actual story. That'd be fun.
So actually finding GPT-2 with like one of the comments from one of the channels. I fine-tuned it on the entire channel comments, but then I gave it the prompt of one random comment, and it doesn't spit out the comment completely. It generates new stuff.
Nice.
So yeah,
because since we have this model, you can continue, because you can get the pre-train rates, but you can continue to train this. So you can train it on your specific like data set you want. So like, because we have the entirety of Project Gutenberg, we could download all of the text and make like a storyteller AI, right? We could have it learn on a bunch of like literature and then say, hey, generate more literature to us, and then see what it does. Which, interestingly enough, that was actually one of the things that they found Chat GPT 4 couldn't do, was it couldn't write stories or poetry very well, because it was like it could state like events happening, but it didn't understand like, you know, the art of storytelling or the art of literature. But I think people have made like storytelling like bots and AI where you have to train it on narrative so it can learn.
Can produce poems actually.
Yeah, are they good poems?
They are like, okay.
They're very like matter of fact poems, really.
So it would try to match the rhythm.
Yeah.
What do you call it? The
cadence or the structure, or
yeah, the structure. The ending words would be similar sounding words. So
like it knows how to rhyme.
Yeah, but it won't be that good. It would write random stuff like this.
Yeah, interesting. Yeah, so this is just our just a little slice of natural language processing, even though everything we said is now out of date as of like 2 or 3 years ago with the advent of large language models. I think you get a overall idea of like, what do you need to do to turn, you know, human text into something that's computer intelligible. So yeah, do we have any?
And if you want to learn natural language processing, you have to begin from the start.
Yeah, you need to start. You can't just like, oh, here's GPT, like it'll do everything. No. Yeah. Start with a text like this, learn how to clean it up and give it to a computer in an intelligible way. So yeah, do we have any questions on natural language processing? Very interesting field. Yeah. Yeah. How big of a model is GPT-2? Like, what's the size? How long did it take you to download?
I don't know how to do that, but
yeah.
It's not more than like 1 GB for sure. It's not
okay.
Yeah. Parameters I forgot.
Because I remember I downloaded Roberta Large, and it was something like it has like 200 million weights in that, like in that model. Yeah. And so for my thesis, I was using Roberta Large, which is what is that Facebook or something? Yeah. So Facebook's large language model to do my sentiment analysis, and I had like 175,000 internet comments for it to analyze, which it only takes in like 512 characters at a time. So I had to break it up sentence by sentence. So I had like 1.5 million sentences to do sentiment analysis on, and I had to run my computer for 3 days straight for it to do the sentiment analysis on 1.5 million, sentences, because every time it was doing inference on a large language model, which was literally doing, if it's 200 weights, right? You think that's at least, or not 200 million weights. That's at least 200 million computations, but actually it's more because all those weights are really inside of a function, right? So
GPT-2 has 1.5
billion.
Yeah.
Nice. Wait.
5 billion model is.
Oh, I mean, it's doing well. Like it's grammatically correct. It's preserving sentence structure. It is within some amount of context of the 10 lines we gave it. So yeah, pretty good. Unlike if anyone remembers the RNN, it was like drunk text. It was like you saw words sometimes the words were
It looked like English if you didn't pay attention.
if you didn't pay it. Oh, but this is actually English. Okay. Yeah, thanks everyone. This is our last official meeting for the year.